Welcome back. Now I want to tell you a bit more about how to actually run a simulation with this Navier-Stokes model. The slide we had before, this is the overview. I hope that by now you have at least a rough idea of what these different terms mean. Right, this is the advection part. This is the motion, moving particles of our fluid in space. And on the right hand side here we have the force terms, the pressure, right, I hope you remember, pushing against the fluid, viscosity, the internal friction, honey versus water, and we have these external forces, gravity, like before. We didn't talk much about this second equation yet so far. We'll come back to that later on, right? Conservation of mass is actually, well, sounds maybe a bit abstract. It's actually very simple to imagine. Before, for rigid bodies, we had a conservation of momentum, right, for the impulse, for example. And here, what turns out to be crucial is conservation of mass. It's actually very simple. It just means nothing can just appear or disappear. Turns out when we simulate things, this is actually not so simple to guarantee. This can be tricky. All right, now another word, actually a more detailed word about Eulerian versus Lagrangian viewpoints. I had it on the slides briefly before, I mentioned it. But what is hiding behind these weird names? Well, turns out what's commonly attributed to Mr. Lagrange is that we basically take a particle viewpoint. What the description I made before for the fluids also in a way already used. We're basically taking a small volume blob or piece of material and then along with that blob track its properties. Right, so in a way the corresponding viewpoint is taking a particle viewpoint. This contrasts with the Eulerian viewpoint. Right? This is commonly attributed to Mr. Euler. Here we basically take a something like a grid, or at least a fixed position in space, and then measure how the same properties or functions change at these fixed points in space. So this is actually what we used a lot in the last lecture on PDEs. In many cases it's somehow a more convenient representation, but things become more complicated if we have a lot of motions, like we have in many of our simulations. So actually one way to think of this Eulerian representation is you have something like a lighthouse or tower that's fixed in one spot, and you look around and see how the weather or temperature or something is changing at that one position in time. Whereas for the particle viewpoint, right, you're basically flying along with the air instead of being fixed in one spot. Yeah, so they actually both have their pros and cons. Right, so for Euler especially, if we have something like a motion, we kind of have to recompute at these fixed spots how the quantities change. You can imagine if we have something that actually moves very slowly on this grid, then we just have very slight changes. At one point might go down a bit, the other one might go up over time. With that we basically have a movement in one direction. However, like so often, there are also big advantages. If you have to calculate these derivatives, like a pressure gradient, that in a way is very easy and very accurate to do on a grid. Like discussed last time, we can take the difference of two values with a finite difference, for example, that directly gives us the tangent, and we can use that to compute a gradient. However, right, we'll actually stick to the particles in the following. Yeah, coming back to this conservation of mass point, this in a way is a bit more easy to imagine why this is important if we have this grid-based viewpoint. So if we look at a certain cell in our grid, and we imagine we have basically we have a quantity that tracks the mass in each of the grid cells, then what conservation of mass means that if we look at a whole system, so all of the cells we have overall, and we integrate, so we basically sum up all the masses we have, that needs to be constant. So I have an example here, a little grid. Let's imagine we have a few mass values of 1.9, 1, and so on. Then this has to be preserved overall, and one way to do that is in terms of a motion, right? You could always just look at the total sum and set it to something, but if we have something like a motion, it actually means if we look at a certain region, everything that goes into the region must somewhere at its boundary leave again, right? Then we have a flux in, a flux out. If they're equal, we're actually conserving the mass within that region. And yeah, one simple way to imagine this is if we are on a grid, say one cell ij, and we have a few fluxes into our cell on the sides of our of this little cube, for example 1, 2, and 4 from different sides. Well, then what has to happen in this case on the left side of that cell? You can imagine for a moment what has to happen if I want to conserve the mass here in this scenario. Well, I in total have 7 units of material, whatever that is, we unitless here, that come in. Hence, all 7 units actually have to leave the cell on that left side. Yeah, so this is actually now a intuitive viewpoint of this divergence that I also mentioned briefly last time. We can actually write this in this vector notation as nabla.u, right? Hope you remember, first part is a gradient. .u means we're taking the gradient of the x component plus the x derivative of the x velocity plus the y derivative of the y component of the velocity. If we have the z derivative of the z component. And for conserving mass, all this together actually needs to be 0. Meaning, right, basically the difference along x plus the difference along y, that has to add up to 0, which is exactly what I had on the slide before with the fluxes in. And now from this divergence we can distinguish different situations. For example, a sink would probably look like something like this. We basically have velocities that in a way collide and move into each other. And as you can imagine, if I move something in here, it will basically shrink, go towards the center, and lose mass. So this may not happen, right? This is not allowed. This would just delete material. And the same in the other direction would just create something. So the big difference here is we're having this Eulerian viewpoint, right? If I have particles that are just isolated points, they can move freely. But if I think of this as a full surface, as something that's really covered, in this case the screen area, then if I move together, I basically shrink the area, and then if I have a constant density for that area, means I'm also losing mass. Yeah, what actually does work, what's also important to point out is if I want to conserve mass, any kind of rotation perfectly does that. Right? So if I motion like the one indicated down here, where this point is standing still, things are kind of swirling or circling around that center point, then that is valid. That does not delete or create anything, but just rotates. And hence, these kind of motions are actually something that fluids end up doing because of this conservation of mass constraint. Yeah, so as mentioned before, we don't want to use a grid, but we want to use a Lagrangian viewpoint with particles, which means instead of these cells in a fixed spot, we have particles which where each of them has a mass. And now, in a way, this conservation of mass becomes trivial, because if we have a certain collection of particles, we can move them anywhere. As long as we don't change their masses, they will just conserve the mass, right? As long as you don't just lose a particle, which in the computer, we have a bug, it can easily happen, but assuming we don't have bugs, we don't lose any particles in implementation, and hence, come back to a similar example. Right, if I have a collection of particles representing this case from the grid before, then it's very easy to just move around these particles anywhere I want and track their masses, make sure they don't change over time. So this conservation of mass constraint, divergence being equal to 0, is actually crucial for Eulerian representations. For the SPH viewpoint we're taking, this is trivial. However, as we'll see, we will have a slightly different challenge or difficulty later on. Yeah, so let's come to the smooth particle hydrodynamics, or SPH in short. They were actually kind of invented or discovered by Monaghan and Lucy in 77, and initially they're motivated by astrophysics, so by basically stars or masses, larger mass, kind of masses represented as points in space that exert forces on each other, and then you also in space actually get sometimes rotating motions and kind of different stars and masses collapsing into each other. And these kinds of effects were simulated with this approach initially, and then they noticed that it's actually also a very powerful description for fluids. So, in terms of time integration, we don't need to worry too much. We'll actually just use an Euler step here. As you see, the main job is to calculate these forces, and because that's fairly expensive, often we'll stick to a simple time integration scheme. Yeah, a few words about the notation. You can use this as a bit of a cheat sheet for the following. Where you have position x, in this case a velocity v. We'll have kernels, I'll come to that in a moment, with a weight w, and then the rest is relatively standard. We have a mass m, a density rho, pressure has not changed, and then also we'll actually look a bit as normals, and viscosity as before has this coefficient nu. Alright, so for smooth particle hydrodynamics, in a way the crucial bit is this kernel function that I've briefly mentioned before, because we have these point masses, so individual points. However, we really want to simulate or represent something that is continuous, right? That fills a larger region. And now the trick is we basically use these smoothing kernels W to extend and interpolate values on the particles. And here you can already see a 2D view of such a kernel. So if you imagine we're in the plane here, and there's one particle here at the center, right at this point, then this particle gets into the space surrounding it a certain weighting function that is peaking at its actual position and falling off smoothly with a gradual fall off towards the sides. And in practice also typically we will actually have cut it off at a certain distance to make sure we don't need to go all the way to infinity. This is more of a practical concern. Alright, so here you now have a 1D example. If you look at the picture on the right here initially, so here we have 3 particles now. There's actually one at 0, one here at roughly 3, and another one at 5. And each of them has a certain peak kernel function. And now we want to use these kernels to smoothly interpolate a certain quantity A. So it's called attribute here. This is intentional, that it's a bit abstract here. This attribute could be anything for now. It could be a temperature or a color or something. We'll get into the details later. For now, it actually does not matter what it is. The most important thing now is how to evaluate this kernel function and how to interpolate something with it. So let me explain what happens here. If we want to evaluate this attribute with a certain kernel W at a position x, this position x could now, in this 1D case, be any position along this line. What we're doing is we are summing all the contributions from all particles. Right? Some of these weighting functions might be 0, then they don't contribute at all. All the ones that are non-zero will contribute to a certain point. Then each of the particles has its own attribute A, AI here in this case. And we now interpolate in the following way. We evaluate this kernel function W with the difference, the distance to the current point. So x is the position that interests us, and then we have a particle I at position xi. Right, so this is the distance, and typically this kernel is radially symmetric, so it just depends on the distance from the position x. And like shown here, we have a certain position, and moving away from it, this kernel will fall off, but it doesn't matter whether we're left or right. It's just the distance to the point of the particle itself. So this is what's happening here. That gives us this weighting. And now we have an additional factor here that uses the mass of the own particle and divides it by the density of that particle. So this is actually, in a way, a normalization of the contributions. So you might now ask, where does this density come from? This density is coming from essentially the same formulation, just basically mapping the mass of the particles into the grid. So the density at a position x is actually given by the sum of just the mass of a particle times the kernel function. Right here, here you have the x position. And now if we evaluate this row at the position xi, that's what's denoted here as a row I. So basically the same process, just for the mass of the particle. This is typically a first step. Let's clean up here, and then once we have that, we can use the density of a particle here for this normalization step, basically reducing the contribution of particles that are in a very dense area, that have a high clustering of particles. Yeah, so that's already what you see here on the right side now with this picture in red. This upper curve, that's now evaluating this accumulated contribution of these 3 particles in the example along space, in this case along the 1D line. Now let's come to the second part of that slide. One neat property of this construction is that if we need the gradient of such a function, the gradient actually is a linear operator, and if we want the gradient of something like this attribute, right, you can basically imagine putting a gradient in front of this, we can actually pull it into the equation, into the sum, and consider the gradient of this weighting function instead of trying to compute the gradient of the whole sum here. And on first sight, that might not look so convenient, but what we can now do here is we can choose function w for this kernel, where we can analytically or easily compute the gradient. So later on, this gradient of w is actually something we can quite easily get. You can actually think of it as just a different w. It typically has a direction, right? Remember, the gradient basically turns something scalar, a scalar attribute, in something with a direction. But, right, so this typically will give us a vector, whereas this is just some kind of point scalar quantity. But beyond that, as you can see down here, the whole expression is exactly the same as above. Right? We have this mass over density term and then times the attribute and the sum over I. It's just this part that changes. All right. Now, what's this w? Let's look at some choices. There are a few popular kernels. So this one is a popular one. It's a cubic spline. Just to illustrate what's typically happening here, we typically have some normalization factor. Ideally, we want these to be normalized, to integrate to 1, and we want them to be finite, right? So they shouldn't extend to infinity. And in this case, right, that happens actually for a distance q. In this case, it's larger than 2. And then here for this cubic spline, we basically have two parts. From 0 to 1, we take this expression, and then from the region 1 to 2, we have this. That basically gives us these two parts of a peak and a fall off on the outer side. Then beyond 2, we'll just we keep a constant 0. Now, this is a common choice. You can simulate a lot with that already. However, in practice, there are slight variations. I have some more examples in a moment. So looking ahead, if you're actually interested in using these simulations in your final project for the exercises, then we actually recommend these kernels that you see here. This is the cubic spline kernel pretty much from before, just written out here, right? So the q is actually now the distance between the points divided by some scaling constant, so that gives you this d specifies how far you set one unit within this kernel evaluation. And then if you want to work with this, as mentioned before, we also need the gradient of that. And this is now given by this expression. So here we have a different kind of kernel function for the scaling away from the center with a different normalization constant. And here in the middle, we now, because this is actually this has a direction, this is a vector quantity, this is a normal vector. So you basically compute a normal vector between xi and x and then scale it with this fall off. Right, you don't need to learn these by heart. This is just something that would come in handy if you want to implement this. Yeah, so here is this now illustrated for with a small example. So what this essentially does is it actually gives you, right, this part gives you a vector towards the center, right? If we have a particle here, it gives you a vector to the center, and then this is a scaling from the fall off of your kernel for the derivative. And what we get out here is actually a vector that essentially tells us within the plane, of course, it's a 2D vector, but how much or in which direction and by how much this kernel function is changing within the plane. So this picture has this error just for illustration purposes, right? It basically gives us a tangent towards the increasing values of this kernel function. If you look at simulations in a bit more detail, what you'll see is there's a whole variety of different kernel functions that are used, because this is a bit of a freedom that we have. And what in practice turns out to be useful is that we choose kernels that are actually fast to evaluate and that allow us to compute these derivatives. So here this is actually drawn, right? So here we have the main kernel. The first derivatives actually look like this, right? So it's 0 at the top and then they increase for these two parts outwards. And sometimes we also need the second derivative, which then would be this bottom line here. Yeah. So one thing that is also popular in some cases is this polynomial function. This one's neat, for example, because it only depends on squared values. It has a squared d constant for the size and another squared distance. And if you look at this, here we actually don't even need to compute, right? We can just remove the magnitude of that and just work with the squared length of these vectors. So we don't need any square root calculations. This is a kernel that can be evaluated quite quickly. And this is something you could potentially pre-compute. So this kernel has advantages in terms of efficiency. Yeah, and then here we now have the some different kernels that are kind of advertised in some of the SPH literature. So this is the kind of normal one that I just mentioned. This is, for example, used for the densities. Then some papers promote this one here for pressure, for example, to have a kind of peaked response in the middle, and something like this, that is where also the second derivative is positive for something like surface tension. Yeah. All right, so to summarize so far, I've explained the general setup of SPH, right? We have these particles with their kernel functions, and I've explained how we can now go in and evaluate some attribute by summation over the contributions from all the particles weighted by their kernel functions. And because these kernel functions in practice have a limited distance, in the example I gave, we had the scaling constant d for the distance, and it basically was 0 at 2d. So afterwards, we don't care, but all particles within a radius of 2d potentially interact and influence each other. Yeah, so now, based on these kernel functions, we can now go in and get started to actually evaluate the pressure and viscosity forces that I've mentioned before.